Okay.
Okay, so I'm mute now. Okay, so now I have to speak here.
I think it's from the
From the laptop. Okay. This connection is working.
sorry.
Test. But are we sure that they can hear us online? You will check. Okay. Okay, great. Okay, so hi everybody. So my name is Paul Boniol. So right now I'm a postdoc in Paris, so in Université Paris-Cité. And I worked during my PhD, even a little bit before, mainly on time series analysis and anomaly detection. So this is why I'm here, basically. And I will present you some work we did during the last 5 years with so Themis Palpanas, which was my supervisor during my PhD, and John Paparizzos from the Ohio State University. Okay, so this talk is try to give an overview of what have been done on time series anomaly detection mostly on the data mining and data management community. So like what method have been proposed, what benchmark have been proposed, and what kind of evaluation we can actually propose can do. Okay, so we will I will try to go over some not so precise details, so give like an overview. But if you have any question, you can ask it. I think it's better if you can ask it now instead of waiting for the end. So if you have a question, you can ask. All right, so first thing. Okay. All right. So time series is something that you can find in almost every kind of domains. So this is, for instance, you find a lot of time series in the energy production domain. So in every kind of power plant, so nuclear power plants, eolians, dams, things, so you can find a lot of sensors, measurements that measure points over time and create a lot of time series. Then you can find them in astrophysics. For instance, here, this is Virgo interferometer in Pisa. So this is something that measure gravitational waves. So try to detect gravitational waves. So this kind of experiments generate a lot of time series. So at least 2 terabytes per day in multivariate time series. So a lot of sensors. Then you have medical applications. So medical applications, this can be like on the like all the machines that monitor your health, but also like robots that generate a lot of telemetry measurements, and then you can analyze these measurements to try to detect things, do some kind of analytics. And finally, another kind of domain is volcanology, so geoscience in general. So here, this is a Piton de la Fournaise in La Réunion, so in the south, in the island close to Africa. And in these sensors, so researchers position like a lot of small sensors around the volcano to measure and monitor what is happening in the volcano. So here you can see, for instance, a multivariate time series from a nuclear power plant in France. So these are like 128 sensors measuring what is happening. So the pressure, the temperature, everything that is happening at the power plant on the secondary circuit. So like not the core, but like the thing that brings the water to hit the turbine and make the turbine turn. So this is the same. So this is like fiber acoustic sensors in the Virgo interferometer in this thing. And this thing tries to detect noise, what happens. So one thing interesting is that to detect gravitational wave, you need very quiet environment. So you need to detect every kind of noise. So here again, this is a time series and trying to detect things that can happen in the building. 400 dimension, again, long time period. Here you see like telemetry measurements from the Da Vinci surgery robot, so the thing that was in picture here. So here this is like the position of the end of the surgery, of the surgeon, the one in the robots, and like all the movements, rotation, angle, and everything. So this also generates like a lot of information, a lot of kind of time series on a lot of different sensors. And this was performed for one specific action of the surgeon. And here are some of the sensors that I talked to you about previously. So some sensors positioned on the volcano. So these are like GPS sensors. So the GPS are on the volcano, and when the volcano starts to move a little bit, so this might be a precursor of an eruption. So this is something interesting to analyze also. So anomaly, so these are time series, and anomaly detection is one of the tasks you can do on time series. So anomaly detection is very useful for many applications. So one application here related to the energy production domain is to detect precursors of unwanted events. So here are some precursors of vibrations in the power plant that we want to avoid. So anomaly detection in time series is kind of trying to detect this kind of events, so unusual events in time, and trying to identify some kind of patterns that could be interesting for the user, for the engineers. Then it can be, as I said, noise detection in the Virgo interferometer room. So here, this is the north building of the Virgo interferometer. So this is a fiber that measures the data. And then we want to detect every kind of noise in here. So the engineers, okay, they monitor everything. And then when there is a noise, okay, they try to detect it and make sure that it doesn't interfere with the experiment and the detection of gravitational waves. So this is one type of action of a surgeon on this robot. So you see like the two different graphs of the machine. And then, when the surgeons do something, it's kind of interesting, also very important to identify wrong gestures. So you can compare with good gestures and try to see on the sensor measurement if there are like some patterns, some sub-events that could be damageful for the patient for the surgery. And here, the obvious application for volcanology is to predict eruptions. Okay, so it's to try to find some weak signals, some subsequences that could be interesting to predict in the future if an eruption will arise. Okay, so this is also time series anomaly detection. So all these domains, so very different from energy, astrophysics, medicine, geology. So they all rely on analyzing time series and trying to detect events, detect subsequences in it. So this is what I will try to show. So on the general specs, not like on the application part, but trying to show you what kind of method we can use actually to solve this kind of problems. So these are actually problems I worked on. So if you have questions, actually a specific question on these topics, you can also ask. And but I will stay more generic in this presentation, so trying to go for more specific, more generic details. Okay, so let's start very general. So I talked about time series, but let's be sure that everybody knows here what is a time series. So the time series is a sequence of points ordered in time. Okay, so this is something that will evolve in time, 1 point per point, and create like one time series. So here, this is the number of taxi passengers in New York City. So I think, I'm not exactly sure, but I think it's 1 point every half an hour. Okay, so this is a time series here. So what we could be interested in are subsequences. Okay, so a point is one value, but a subsequences is like a subpart, a small portion of the time series. Here we see like 4 consecutive days of the number of taxi passengers in New York. Okay, so you see like the night, then the morning, the first rush hour, then the lunch break, and it continues. So you see patterns. So analyzing these subsequences can be very interesting. So trying to find abnormal patterns, abnormal subsequences. So now let's talk a little bit of what is an anomaly. So the problem is it's very difficult to define properly and formally what is an anomaly. There is no clear definition of it. So for an engineer, this would be something like a failure in the machine. For an astrophysicist in Virgo, it would be a noise. So there is no clear definition of what is an anomaly. And this is actually a big problem for our domain, because it's very difficult to define an objective function, because we cannot define it properly. And this is maybe why, we'll see it later, deep learning methods are not completely outperforming the classical method in this domain, okay? So what we define as an anomaly is a rare point or a rare subsequence. Rare means something unusual. So it can be a real anomaly, like, I don't know, like here we see, for example, the daylight saving time. So this is like clearly an outlier. So you add 1 more hour, so you have more taxi passenger, but this is an anomaly. It can be like environmental events, like a flooding or a snowstorms that have a strong impact on the number of passengers. So this example was also taken by Juliana during the keynote. So this is, I think, the same data. But it can also be not real anomaly. It can be Christmas, for instance. So here you see this is the biggest anomaly of the time series. When you look at this time series, you can clearly see that this is mostly maybe the most abnormal subsequence, but this is Christmas. So it's not really an anomaly, but it's something unusual. So we want actually, we will define it, we will consider it in our case as an anomaly. Okay. So then how do you detect them? So the point, an anomaly detection method, so every anomaly detection method will try to build an anomaly score. Okay, so an anomaly score is moving from the time series and then computing a value between 0 and 1. And the closer to 1 it is, the more abnormal it is. It should be, at least considered by the methods. So the objective is to build this kind of anomaly score. And then you can compute a threshold and say that everything above will be returned to the user, considered as an anomaly. Okay, so here we see that it might be correct, like the daylight saving time, but also like some false positives, like Christmas here, or I think this was a Martin Luther King Day, and this is a Labor Day, so some kind of other like regular events. All right, so in this talk, I will start by defining, giving some example of what are the types of time series we can have in our domain, what types of anomalies also we can encounter. Then I will give you a brief overview of the taxonomy of the methods that have been proposed in the last 10 years, well, actually even more, 30 years, 50 years, and some existing benchmarks, so recent benchmarks that have been proposed to evaluate compare methods. So this is very important, and I will try to spend a little bit of time here. And finally, also a very important point is how do we evaluate, how do we compare anomaly detection methods, and trying to go over like metrics, measures, that you can use to compare the accuracy of the different methods and see some kind of challenges related to time series and anomaly detection. Okay, so let's start with the foundation. So, we say, so there is two different types of time series. So there is like there are like univariate time series. So univariate time series means one dimension. And you will have only like to look at the points in one dimension. And then we say that the length of the time series is written as here. So if you see in the presentation, something like that, I mean the number of points in the time series, so the length of the time series. Then you might have multivariate time series. So multivariate means when you have multiple dimensions, and it could be like multiple sensors, different things. But what you have to know is that one point is actually a vector, so it's a multidimensional point evolving in time. Okay, and then time series can be also like non-stationary or stationary, but we can also say like single normality or multiple normality. So here, okay, here we have an anomaly, but then like the normal behavior is consistent in time, so always the same. But it might happen that sometimes the normal behavior also change. And this is something that we need to take into account in the method we propose. So you might have something like normal for one day, and then the next day something abnormal, but then it starts to be normal. So the time series evolves. So this is even more important for very long time series. So for instance, IoT measurements. So if you have like a watch, and then you start to walk, and then you start to run, this will not be the same pattern, but this will still be normal. So this is like a change of normality, and you have to catch this kind of thing. So when I mean multiple normalities, I mean exactly this. So change in normality in time series. So you can also say non-stationarity or stationarity, but this is more like a statistical meaning. Here it's clear. I mean, it's easier to understand what I mean by multiple normality. Okay, so let's talk now about anomalies. So an anomaly can be first a point. Okay, so a point is like a value that is outside a given distribution, a given normal distribution. So in this kind of cases, it's kind of easy to look at, to identify these points. Okay, so you just look at the tail of the distribution, or even like just find a threshold that can detect the abnormal values. But these points as anomaly can be also contextual. So it might be a point anomaly, but in a given context, so in a given window. So here, in this distribution here, okay, it's an anomaly. But then when you look at the global context, well, it's not an anomaly anymore. It's like it's in the range of value of these points here. So this is also like an important type of anomaly to handle. So contextual point anomaly. Then, so this is an example here. So this is from the Yahoo benchmark. So a very famous benchmark for time series. So you see that there is a trend, linear trend that decreases. There is an abnormal point. So this is contextual. So if you look at the global distribution of the time series, you won't see it. You need to look at the local distribution around the anomaly to actually identify the abnormal point here. And then, very important, we have subsequent anomaly or collective anomaly. So these are different terms for the same thing. So a subsequent anomaly is like an abnormal evolution of points. So even though all the points of the subsequence might be normal, so in the normal distribution, then this is the evolution of these points that are important to look at to identify the anomaly. So here we can use like distance measurements to like compute to identify different shapes, and the anomaly will be based on the shape of these points. So this is an example from the MGAB benchmark. So you see that well, you have to trust me because these extreme points are like not value issues, but this is a shape. So here you see that there is like a regular shape, and then there is something different that happens. This is like a collective anomaly. This is a subsequent anomaly. And then also another important point is the cardinality of the anomaly in the time series. Okay, so in one cases, you might have only one anomaly in the time series. Okay, so you have like 10,000 points, one anomaly. Okay, this might be easy to detect, not all the time, but okay, so you have to detect only one event. But then also you might have different types of anomalies in the same time series. So you might have points anomalies and sequences anomalies. And here, it's quite important actually to have methods that can work both on point and sequences. And even important, most importantly, you can have like a repetitive similar anomaly over time. So subsequences with like very close nearest neighbor distance, or something that repeat over time, might still be abnormal in terms of rare events. Okay, so this cardinality is also something interesting to look at. So these are examples. So here, this is like one single anomaly on a time series, and here you see from the SVDB benchmark dataset. This is an electrocardiogram, and this is actually the case in many electrocardiograms. When you have an arrhythmia, in red here, this arrhythmia might happen over time multiple times. Okay, so these are like one very specific case of similar anomaly, recurrent similar anomaly over time. Okay, so now, so if you have any question, feel free to ask. So I will move on the methods part. So I described what is a time series, what types of time series we have, what type of anomaly we can also have in the time series. So now let's try to see what kind of methods have been proposed in the recent years. So a method, so just a reminder, is a function that will take some parameter, and from the time series will compute an anomaly score. Okay, so what is important is then to look at what kind of parameters this function needs to operate. Okay, so first thing is like we can actually like propose a taxonomy of methods by domain, by community. Okay, so anomaly detection is something very old. So people propose methods like since the 60s, even better, even before. So like there exists a lot of statistics methods to detect outliers, to detect anomalies. So these are like examples of these anomalies. Then stochastic learning, in the stochastic learning community, they propose also like a lot of methods. So like hidden Markov models, for instance, are like one of these kind of methods. You also have like in signal analysis. So in the signal community, they propose also some kind of different methods. In the outlier detection community, so LOF, isolation forest, like all these methods. In the machine learning community, so machine learning like one class SVM. So machine learning also proposes like a lot of methods for anomaly detection. In the data mining community, so data mining community, this is basically the KDD, ICDM, VLDB, Sigma ICD community. So I've been quite active in this domain as well. So propose like a lot of different methods. And of course, deep learning that for the last 5 years, many methods have been proposed. It's quite difficult sometimes to keep the pace of reading all these papers that come out with, that are published. But I mean, these are like a big overview of all the methods proposed in the literature. So this figure is not from me. I have to acknowledge. So this is from Sebastian, Philippe, and Frosten. So this is a paper in VLDB 2022. As they did like a quite exhaustive list and enumeration of methods proposed for anomaly detection. So this picture actually illustrates well how dynamic is this domain. I mean, this is very difficult actually to go over everything and compare everything, but this is very also challenging, very interesting. So this kind of taxonomy are not that useful. So now let's try to compare to classify the method based first on the parameter, on the input they take. So a first thing that you need to know is that some methods are supervised. So supervised means that they need examples of anomaly or normal subsequences to detect, then to compute an anomaly score. So they will train to basically classify the anomaly from the normal behavior. Okay, so these are like a specific type. So this is closer to classification than anomaly detection, but it can still be used for anomaly detection. So some methods are supervised. Then most of the methods proposed in the literature are semi-supervised. So semi-supervised means that in this case, we don't have anomaly examples. And this is kind of realistic because in many applications, it's difficult to find this kind of examples for anomaly. So most of the time, it's easier to find some example of the normal behavior. And we can build a model to detect correctly the normal behavior. And then by failing to detect the normal behavior, we can detect the anomaly. So these are semi-supervised approaches. And then there are like the unsupervised approach. So this is simple. There is nothing as a input, as data. So you take just the time series, some user-defined parameter, and then you compute an anomaly score. So I will present mostly semi-supervised and unsupervised methods, but also with a big focus on unsupervised methods, because this was like where I worked mostly on unsupervised, so I'm more familiar with all these methods. And also this is very important in my opinion here, is that even the normal behavior sometimes is very difficult to define. It's not easy to have examples of like experts, engineers saying, okay, here I'm sure 100% that there is no anomaly. Even this is kind of difficult. So unsupervised methods are very useful in many applications. Okay, now let's try to propose another taxonomy, but this time based on how the method work. Okay, so we have like a first big category of methods, which are like distance-based methods. Okay, so distance-based methods is just like trying to compute distances and then identify the anomalies based on this distance value. So you have like the discord-based approaches. So these are like a big literature on it, and cluster-based approaches. So I will go into details after that on how they work exactly. Then you have like density-based approach. So this is like a very generic term, but density-based means that you will try to model, to evaluate the density of the subsequences of the points, and then trying to identify a low density part of the time series. So you can do it in different ways. So there are like tree-based approach. So like isolation forest is an example, graph-based approach, so series to graph, and distribution-based approach. So when you can try, for instance, to build histograms, and HOBS, right, is one of, I think it's HBOS, this is a mistake, when you build histograms to detect abnormal values. And then you have prediction-based approach. In this case, these methods are mainly semi-supervised because the idea is to predict something. So you can either forecast the next value. So it's forecast-based approach. So you have like one subsequence, and then you try to predict the next one. And then you go on and you use the prediction error to detect the anomaly. And then there are reconstruction-based. In this case, you take the subsequence and you try to reconstruct it. Okay. And this reconstruction will be used. So this reconstruction error will be used as an anomaly score. So I will now go into some examples and to describe more in detail all of this category. Yes.
Are there ensemble of these methods?
This is a very good question. Well, it's like very recent now. People are starting to work now on trying to ensembling them. So there exists like AutoML solutions, for instance, that try to do model selection. So like one example is MetaOD that have been proposed. I think it was a KDD or maybe iClear 2019 that try to do model selection. So you can actually have like a pool of methods and then try to select the different method. So there is possibility. And then there are ensembling also approach for outlier detection. So there is like a lot of work by Agrawal on this thing. So A simple way would be to do the average of all the anomaly score. So you run everything and you do the average or the max. So there are possibilities. But for time series, it's still, in my opinion, it's still like ongoing work. I mean, there is still progress to.
Because in the classification community, there's like a big thing about Anomaly, right?
Right.
Yeah. Methods.
Yeah. So I've quote is the one of the big example. Even in session time or like ensembling multiple convolutional network. I think it's a target actually to reach here would be to propose like an ensembling approach in the end. But I have some slides at the end about this exactly. So this is a nice point here. Any other questions? No. Okay. So let's start with the distance-based approach. So as I said, distance-based, it's in the name, you compute distance. Distance between subsequences. So the objective is, okay, for one given subsequence of the time series, then you can, based on other subsequences of the time series, compute a distance score, a distance value, and use it as an anomaly score. So you can, it can be, for instance, taking the nearest neighbor. The nearest neighbor, you compute the distance to the nearest neighbor, and the one that have like a high nearest neighbor distance could be considered as an anomaly. So this is Discord-based approach that are doing this. You can also do like the k nearest neighbor. So instead of looking at the first neighbor, you look at the k one. So this is in order to avoid the problem of similar subsequences, so similar anomaly over time. And you can also do like, okay, let's do clustering over all the possible subsequences, and then let's try to find the nearest cluster, and then compute the distance to the nearest cluster. Okay, so distance-based are like grouping all these methods that try to compute distances for subsequences. Okay, so then you use this distance computation to identify the anomalies. So here you have like an electrocardiogram, these are arrhythmia, and you can compute the distance and say, okay, identify the arrhythmia correctly. So by distance, you can use many kind of distance methods. So the most common one are like Euclidean distance. So this is very simple. You just compute the distance point per point for the subsequence. You can also do DTW, so dynamic time wrapping distance. So here you care a little bit more about the alignment, so trying to find the best alignment possible to minimize the distance. The good point of Euclidean is that it's more scalable. I mean, it's easier to compute. The complexity is lower. So most of the methods, some of the methods are using Euclidean distance for this reason, specifically for the case of big, large time series. So let's see one example. So one of the methods, very famous method, is matrix profile. Okay, so matrix profile. So it has been proposed in 2016 in ICDM, and matrix profile is computing. So here is this is like a view of a time series. And a point is a subsequence. Okay, so matrix profile will compute the nearest neighbor distance and use the nearest neighbor distance as an anomaly score. So here you see that all the normal subsequences will have like a very low nearest neighbor distance compared to the anomaly in red. Okay, so yeah, so as I said, the anomaly score will be just the nearest neighbor distance for each subsequences of the time series. So here this is an example. So you have like one time series. This is from the NASA benchmark. So this is like a rotary sensor. And then you have like an anomaly here. And this anomaly is correctly identified by matrix profile. Indeed, this is the discord in this time series. And an interesting thing is that also there have been like a lot of work on this. So like extensions have been proposed for streaming time series. So StumpPy, like a very new method has been proposed in 2023. So done. That actually can tackle the problem of recurrent similar anomalies. Then you have left StumpPy that forgot the anomalies that have been discovered in time. Stump for anytime computation. So even though the computation is not done, you can still get a first estimate of the nearest neighbor distance. And mstump for multivariate time series. So this is like a very dynamic research area with a lot of methods proposed. Then you have a method called Norma that has been published in 2021, and this idea is more to work on clusters than only subsequences. So the main idea here is to actually compute like a set of similar subsequences, so clusters, and weight them based on some statistical criteria. So like the number of subsequences within the cluster, the time distribution, and the centrality of the cluster. And then you can define like a distance function of one subsequence to this set of cluster to compute a distance. Okay, so here you can see two examples. So here this is like a normal sequence in the taxi dataset, and here this is an anomaly, so it's no storm. And this thing is quite unlikely to be represented here, or if it is, it will be represented in cluster with a very low weight. So it will have a very low impact on the anomaly score. Okay, so this is one method. So another thing is like a method called SAND have been proposed also for streaming time series. So you can actually update with a new arriving batches of subsequences this model here, so this set of subsequences, to make sure that it can adapt to a change of normality. So as I said, with multiple normality time series. Okay, so now let's discuss a little bit of density-based approach. So density-based approach is just to take the time series and try to represent it in a space and evaluate the density of that space. So it can be either by splitting the space with trees, building histograms for different value of the subsequences, or like the different dimensions, and also build the graph and then try to work on the graph to identify the anomaly. Okay. So I will go over an example of a tree-based approach and a graph-based approach. Okay. So one of the most famous methods for anomaly detection, not only for time series, is isolation forest. Okay. So isolation forest have been published in 2009. So it has been proposed for generic data, not time series, but it's actually working well also for time series. So the idea here is that we will try to split randomly the space. Okay, so here we do a split. Okay, in this split we can say, okay, and then we will try to isolate specific points with splits. Okay, here we say, okay, let's keep only this part. Okay, then you do another split, you get these values, you go on. Here you already isolated one point, so you stop 3 splits, and then here you continue up to 5 splits. So here the idea is that the number of splits you need to reach one point is something that you can use to detect anomalies. So if you need very few splits, it means that the point is very isolated in space. Okay, so this kind of splits can be represented as a tree. Okay, so this is why it's called isolation tree. So here it starts from the entire space, and then you do a split and you go on. Okay, so here you reached one point here. So the depth of this to reach this point is very low, and then you go on for normal points is very high. Okay, so we will actually use the depth of to reach an instance as an anomaly score. Well, actually, a function of this depth to be precise. But the thing is, like as I said, these are random splits, and randomness can be a problem because you might be unlucky and reach like an anomaly with a lot of splits. So what they proposed is that they propose to do it for multiple trees and then do an average, kind of an average for all these depths. And this is how you can identify. So this is a very nice method actually, because the parameter, you have like multiple parameters to control the execution time. So you can control the maximum depth of the tree, the number of trees, of course. And this method, even though proposed for generic table data, is still working well for time series. So this is quite interesting also. And even for subsequences. So now let's look at an example for a graph-based approach. So series to graph, so this is a method published in VLDB 2020. And the idea of series to graph is to model the time series as a graph. Okay, so try to compress all the time series into a small graph on which you can work to identify unusual trajectories that will represent unusual subsequences. So here, from this view of a time series, then you will extract nodes of the graph. So the nodes are similar subsequences. So here, so all the sequences contained in this node will be very similar subsequences in shape. Okay. Then you connect the nodes together, very simple, and these edges are very simple. The weight of these edges correspond to the number of time a subsequence of a given node have been followed by a subsequence of another node. Just this information. And this value is very important because this value is already telling you a lot on the recurrence of the transition, or the frequency of this transition. So if this weight is very low, it means that this trajectory is most likely to be an anomaly in the time series. Okay, so in general, we use two criteria, two statistics of graphs to detect anomalies. So we use the weight, of course, of between nodes, and we also use the degree of the nodes. Okay, degrees of the node are the number of connections in and out, and the higher the degree is, the more central the node is. Okay, so it means that there is like a dense community of nodes that kind of represent like a recurrent evolution of behavior in this community here. Okay, so by using the tool, we can actually compute an anomaly score. So there, a distributed version of this algorithm has also been proposed in published in the EDBT, which is called DATS. So they do this computation of the graph on a distributed way. So it's very scalable actually for very large time series. So this is very nice. So series to graph has been my work, but this is not my work. So, but this is very good work. All right, so let's look at a specific example. So here you see again the NASA time series. You have like this normal pattern going up and down, and then you have like some error here of some anomaly here. So we build the graph here. So so the thickness of the edge is proportional to the weight. Okay, so the more black and thick it is, the more the weight is important. Okay, so here in this graph, then you can compare like a normal subsequence, like in green, like following like this big path here, which is more likely to be normal, actually it is, and then an anomaly, which is actually going into the center with edges and nodes with like a low weight and a low degree. Okay, so this is like how you can actually use this kind of graph-based approach. So this is very useful to detect anomaly, but also on a visual point of view. So you can convert like very long time series into like one graph, and then look at the graph and use it as an interface to say, okay, here this trajectory might be interesting to look at. Okay, so this is also one interesting aspect of this method. Okay, now let's go on with forecasting. Yes.
I have a question on the previous method. Do you use like some kind of clustering in order to do that?
So, yeah, that's a very good question. So I wanted to stay very generic on the philosophy. So no, we don't use clustering. So this is also something very interesting, because the problem with clustering is that you have to set a number of clusters. So you kind of predefine the number of nodes. So there are methods to automatically find the number of clusters. But what we wanted to do is to actually use, so we project all the time series in a reduced space, like in a two-dimensional space that represents the shape of the time series. In this space, we do a radial scan. So this is a parameter, the number of scan you do. So this kind of have an impact in the number of clusters. So this is like a hidden way to choose a number of clusters. But then on each intersection, you will estimate the density of the trajectory. So the trajectory will cross this intersection, and you will do like a kernel density estimation using a Gaussian kernel in this case. And all the local maxima are like the densest intersection, then will correspond to one node. So this is how we build it. So that's a shame that I don't have a slide for this. I should have prepared this question. But so we don't explicitly say we need that many nodes, that many clusters. But we say that we want 30 radial scan. So if you say 5 or 100, then of course you will have like a significant increase in number of nodes. Okay, so this is like as a proxy used as a number of clusters. All right. So these are like two examples. So isolation forest and series to graph for density-based approach. So now let's discuss a little bit about the forecasting-based approach. So the nice thing, so in these two categories, so we'll talk about forecasting and reconstruction. So in this case, what is very interesting is that actually the objective function is clear here, which means that we can use machine learning and deep learning methods. So you can define a loss function that operates in this case. So that's why in these categories, there are like many deep learning methods that have been proposed in the recent years. Okay, so forecasting is easy. The objective is you have as input a subsequence, and you want to predict the next point. You want to predict like either like one point or the next subsequence. Okay, so here you want to minimize the forecasting error, so the mean square error, whatever you want to use. So there is like an objective here, and then you go on. You have this as input, and you reconstruct, and so on and so on. So what is interesting here is that by training on data here, and you can make the assumption that there are few anomalies here. So when an anomaly will arrive, you will fail to predict the next value. You will fail to predict the shape of the subsequence. So then by computing this MSC or this forecasting error, you can actually detect the anomaly. So here the anomaly is here. Okay. So a very basic example are like LSTM-based approach. So LSTM have been like widely used for forecasting. So of course it has been tested for anomaly detection using this kind of framework. So just trying to forecast the time series and use the forecasting error as an anomaly. Another interesting approach used the CNN, convolutional neural network, to do this. So here we have like a subsequence, and then you will have like a first convolutional layer, a max pooling operation, a second convolutional layer, a max pooling operation, and then a dense network that will connect to the next point. Okay. So this is very simple, a simple architecture, but working quite well. And then this thing will slide over the time series and compute this prediction error, this forecasting error for the anomaly score. So what is also very interesting is that these methods are by design also working on multivariate time series, because all these inputs that you can give to a convolutional layer, to a LSTM, you can actually provide a multivariate time series, which is not the case for some of the methods I presented before. So for instance, series to graph is not working for multivariate time series. So these are very interesting methods for this reason also, like working on multivariate. Yes?
Like how large is typically the prediction horizon in these methods? Because you probably don't want to predict with the next point because that's very, very close to the last one you've seen, but you probably want to like detect the point in the 50 data points. Like this.
Yeah, right. So for the LSTM AD paper, I think they did with a horizon of 10 points, if I remember correctly. I don't know, but usually they do 1 point because yeah, because the thing is, and we will see it in the experimental results, is that in their focus, they are focused on points anomaly. So you have like an evolution, and then up, you have like a big change.
Okay.
And you want to say, okay, my next point is this, and then this big change, you detect it. So I think, I mean, I don't want to say any mistake, but I think DeepAnt is actually doing like a 1 point prediction.
Yeah.
But it's very easy to actually do multiple points. You just increase the number of outputs of your layer. Yeah. And for LSTM, it's also, you just increase, you can actually do your, it's even easier. Sorry.
Because I would guess that it's like better for the model to like predict something that lies a little bit more in the future, because it's very trivial to really predict the next point, because the next point will all like in your normal model will always be like very close to you.
Yeah, that's a very good point. Yes, because this would be very helpful for sequence anomaly, yeah. Because you need to predict the next sequence to then compute the distance between the prediction and the sequence. If it's 1 point, then okay, then we do 1 point. But if you have like an arrhythmia like this, then it might be better to say, okay, from this pass, I want to predict the rest, yeah. And then compute this distance. And sorry, this is maybe why actually these methods trained as 1 point are limited for the case of subsequences. But a simple fix would be actually, yes, let's try to increase your horizon, and it could work better. So this is a good point, yes. A question? So last part, I'm in time. Yes, I'm in time. Reconstruction-based approach. So this is a little bit different. So here we still have a time series as input, so no surprise. Then the idea is to reconstruct the subsequence. So you get one sequence here. This is a blue one, and then you try to build a function, a model that will reconstruct. So we give as output the red one here. The reconstruction error will be used as an anomaly score. The philosophy is simple. It's like you train a model on a collection of time series or like a single time series for some subsequences. If your model is able to understand the time series enough to reconstruct it, then it should be something that you've seen a lot in the database, in the data set. If you fail it, that means that it's something very new that the model was not trained on. So it kind of benefits from the fact that it overfit on the normal behavior, and then try to, when a new behavior arrives, you fail. So here you see an anomaly arrives, the model, so these are real results that I computed it. So the model tried to reconstruct it. It fails, so it actually tried to reconstruct something normal. So you see like this kind of evolution is not used to this slow evolution here. And the reconstruction error, of course, will be higher. And you go on and you can use this reconstruction error to detect the anomalies. Okay, so one very, yes, you have a question? No, sorry. So one very basic method to do it is autoencoders. Okay, so autoencoders is you take one time series, again, univariate or multivariate. So these are like the different dimensions of the time series. You put it in an encoder, you get a latent space, so like a reduced, a small space as an input space. And then you train a decoder that will try to reconstruct the time series. So this is done simultaneously of the two. So you use the reconstruction error as a loss. So again, here we have an objective function. So this is why, I mean, all these methods can be proposed. I mean, because they found an objective function that corresponds well to the case of anomaly detection. So here you see the difference. Okay, when you have an anomaly, of course, you fail to reconstruct. Okay, so this approach here published in 2014 used like a simple multi-layer perceptron as encoder and decoder, but you can use convolutional layers to do the encoding and the reconstruction. You can also use LSTM networks, so you can use also recurrent neural networks. So this kind of approach are quite modular. You can actually modify a lot based on your use case and what you want to do. Okay. Okay, so let's now discuss about the benchmarks. So these methods are very interesting, but what is also very interesting is to have like a well-defined set of time series on which you can work and compare and study them. Okay, so in the last 2 years, 3 benchmarks have been proposed. So 2 in VLDB last year, and 1 was ICD, no, maybe KDD in 2021. So the first benchmark is the XUCR benchmark. So the XUCR benchmark is something that has been proposed by a student of Amon and Amon himself. So they organized a competition in KDD 2021 on anomaly detection, and then after the competition, they opened the benchmarks they used for the competition. So this benchmark is composed of 250 time series. So these time series are univariate. So the labels have been manually checked. So what's a good thing with this benchmark is that actually they checked each label, so they are reliable. And but what I did is like each time series contains only 1 labeled anomaly. Okay, so this is the first benchmark that have been proposed. Then the second one is time eval benchmark. So time eval benchmark is the benchmark proposed for the experimental evaluation by so Philippe, Sebastian, and Srosten from Astroplattner Institute. So they collected in total 976 time series, so significantly more. They also created a new synthetic benchmark called Gutentag to tune the parameters. What is great here is that Gutentag is, yeah, they are German, so so the labels are reliable here, so they can actually tune the parameter and be sure that they don't tune on the labels that might be questionable, let's say. But then they filtered a lot of time series. So actually they collected way more than 900. 900 is the result of the filtering. So they filter the time series such that the contamination rate is lower than 0.1. So contamination rate means the ratio between normal and abnormal points. Okay, so they do not consider time series with a contamination rate above 0.1. And then they kept only time series for which at least one method perform above 0.8 OCROC. So this means that they only kept time series for which at least one method is working well. So this is a way to avoid the fact that, okay, if you have a time series and everybody fails, it might be the case that these time series are like not correctly labeled. So it might also be that all the methods proposed are not working. Yeah? But it's a possibility. There is like a possibility that it's badly labeled. So it's preferable to remove them. So this is where their philosophy in this benchmark. And then there is a TSB UAD benchmark, so proposed in VLDB 2022 also. So these two have been proposed in the same conference. So this benchmark contains 2,000 time series labeled, but the philosophy is different here. So here, the time series have been collected and proposed as proposed in the literature. So this is also my work, so I will say we. We collected multiple time series from different domains, so astrophysics, environmental science, engineering science. So all these domains, and we took them and we took the label proposed by the engineer and we say, okay, these are our benchmark. So we did not filter anything, neither based on the contamination rate. So we have some time series with a high contamination rate, but also very low contamination rate. And we didn't filter also based on the performance of the model. So for some time series, actually, we don't have any models that perform well. So I think it's a nice way also to have like a picture of what we have as time series in the literature. So these are the things we have, and then we can work on them. The size also is a great thing. So we have like a large collection from multiple domains. So these are like one of the benefits. One of the drawbacks, because I also have to say drawbacks, of course, is the fact that, of course, we have less certainty on the quality of the labels compared to the two other ones. So this is, of course, something that you also have to take in mind, keep in mind. But as we propose, so this is the data examples of the time series contained in TSB. You can actually choose this. Okay, let's say that I want to apply. So I'm more focused on ECGs. Okay, let's take like the ECG, SVDB, MITDB, which are like medical data. You can actually choose the data set that corresponds the most to your application, to what you want to evaluate. Then we also propose like some method to generate artificial and synthetic data. So these are for to create like reliable labels and train the model on this kind of unlimited data. Okay, so one way is to actually use the UCR archive for classification, and you concatenate patterns of different classes to generate anomalies. Okay, so then you can create a graph saying, okay, I want this as most repetitive, and then I include these two other classes or two other data sets to create like this artificial data set. You can also inject random walk. So this is a normal one, sorry. Add noises, add outlier points, change the frequency, or like modify the normality to create like multi-normal time series. So these are also interesting ways actually to create and work on synthetic data. But of course, real data is like more challenging. Yes?
What's the difference between your synthetic data generation? Just to know, I'm working on
You're working with on the Guten Tag?
Yeah.
Okay.
No, I'm working on it.
Okay. Well, there is no big difference. Guten Tag is proposing the same. If I remember correctly, Guten Tag, they propose like a set of pre-computed. So they have like this, I think it's 200 time series in Guten Tag, but they gave the code also to generate new time series. So it's not big difference. Well, no, actually, no, it's actually very similar on the way they generate. But the point is the same. Here, we want synthetic data to actually have reliable, to tune the parameter. So, yeah, so these two benchmarks are like propose this way of synthetic time series building and real collection of time series. So now let's try to see, to look at the experimental evaluation that have been conducted on these benchmarks. So these are the results on the time eval benchmark. So this is from their paper. And they compared a lot of number of methods. Actually, this was very impressive. And both semi-supervised and unsupervised. So here, this is OCROC, so area under the curve of the receiver operator curve, I think. Thank you. And what is interesting in this evaluation is two things. First, distance-based approach are working pretty well. So we might think that now that deep learning, is almost 10 years old, actually more than the modern deep learning is more than 10 years old, might be completely outperforming like the old traditional method, but it's not the case here. Sub-LOF, LOF is a method proposed in 2001. Is for on their benchmark, the one that outperform everybody. Sub means subsequent, so they use subsequence. So, and then you have like density-based approach. So here you see SAND, which is the extension of normal in streaming, series 2 graphics here. So you see like, these are like very interesting insights in these results. Then what is also interesting is that semi-supervised, so these methods that contains more information for the training, semi-supervised are not outperforming as an unsupervised approach. So these are also interesting results here. I mean, when you look at this plot, sub-loft are actually better result than the best of the semi-supervised approach. So this is something also interesting. So maybe there is like a very interesting future work on the direction of semi-supervised to make sure to try to, maybe there is like a large margin of improvement here. Because, I mean, in what I believe is that when you have more information to train, it should be better. But actually, it's not really what we observe here. So these are like very interesting results. We can also look at the results on the XUCR benchmark. So I took the result of TSB. So TSB contains UCRX benchmark. So it's included inside. So we can look at the different methods that perform well. Again, we see that distance-based approach are working very well in this case. So matrix profile is a very strong performances, normal also. So this is something interesting. We can look also at the result on TSB UAD, so the big benchmark of 2000 time series. Again, we see then the distance-based approach are working well. So this is something that this is an interesting observation, is that distance-based approach are quite effective, and a nice way for our community is that these approaches are also very scalable. I mean, computing distances is something that we know how to do, and we can do it on a distributed way. You don't have enough any training to do. So I mean, this is something that works well. You can get an answer pretty fast. So that's interesting. Also, isolation forest. Yes. Okay. Isolation forest. So isolation forest and isolation forest 1. So isolation forest takes a subsequence as input. Isolation forest 1 takes a point as input. Okay. And these methods that are not dedicated for time series are still working very well. So this is also something interesting to note here. So if you
benchmarks are most of the time series periodic, because like most of the examples that you've shown is also something that you see in the papers a lot, is that you have like an ECG but an ECG in some sense it's a very like easy time series because it has like one tempo pattern that is repeated all of the time. But then if you look into like other real time series, they may be way more chaotic as they get larger, and they may not be as like regular. So my point is, I would think that a distance-based method is very good when the time series is very periodic, because then they can like relate these tempo patterns quite well. But as they get more chaotic, I would guess that they generate maybe.
Yes, this is a very good point. So in TSB, there are not only periodic time series. So in TSB, you have like something like opportunity or IOPS that are like more like measurements without like any clear patterns. You have, of course, a lot of ECGs, which are periodic or at least cyclic. So KD21 is a XUCR, contains a lot of periodic also time series. So I agree, distance-based approach are, and actually I can say it, I can affirm it, Norma, for instance, is working very well on periodic time series and cyclic time series. So in this specific case, as this benchmark contains maybe, so I don't want to say any wrong numbers, but yeah, I think like a good 20% of this benchmark contains periodic time series. So 20% is maybe over-representing the reality. Maybe it's too much compared to what we have in the use cases. So, but still, I mean, this is something that we observe a lot. So in the examples we saw from the beginning, I mean, if you look at surgeons data, I mean, all the patterns they are doing, so they are not periodic, but they are cyclic. So there are cycles that look similar over time. If you look at sensors data, you have also like different stage of the power plant. So they're like producing energy, not producing half of the energy, and then you have like cycle, okay, go up, go down, and all these things. So you can still observe this, and of course medical data are like very periodic.
So then one quick follow-up: do these time series contain multiple notions of normality? Because we talked about this in the beginning, which are basically like different process states that you capture. Is this your contain, or is this just like one?
So it's very difficult to measure, to check if they contain them. It's very difficult. So what I did for a few of my papers is that actually I synthetically generated them. So I take, for example, one ECGs from one patient and one ECGs for another patient. So the heartbeat is not the same. So you have like a chain of heartbeat, and then you have to capture this evolution of heartbeat. Then what I do is that also I concatenate an ECGs with a smartwatch measurement completely different. And then you measure how the method can adapt to this. But I'm sure there are some examples here containing multiple normality. It's just like I cannot say how many. As I cannot say, it's very difficult also in this benchmark, because in the time eval benchmark, which is nice with the Guten tag, for instance, with the Guten tag, that they add like a category of anomalies. And then they can like measure the performance of the method based on the category of the anomaly. So trend, pattern shift, point outlier, all these things. In this TSB, it's harder. So what we have is like sequence points. So this is easy to check. But knowing that it's a pattern shift or not on real data is harder. So yeah, I mean, all this work are complementary in the end. So that's what I like with this. But yeah, I mean, multi-normality is a problem. And it's difficult to get real examples on which to evaluate. All right, so where I was here. Yes, saying that also autoencoders are working very well, so on TSB, which is interesting also, like good performances for the reconstruction part. So then we can also have like a deeper look on the different categories. So as I said, we cannot differentiate the anomalies based on the shape, like pattern shift, frequency anomaly, things like that, because it's very difficult for time series anomaly. But then we can say, okay, are these time series containing points anomaly or subsequent anomaly? This is easy to check. So we can then measure the difference. And this is very interesting. So here you see a drastic change of performances between point and subsequences. And what is even more impressive is like when you see that CNN here is like the almost perfect, whereas CNN was ranked here for sequence. So this is exactly what was your question, you know, like when you detect the next point, for point anomaly, it's working very well. And actually, this is one of my suggestions. If your anomalies are points, it's better to use actually these forecasting methods. If these are sequences, it's not the case here. It's not working well. LSTM also is working pretty well here, but LSTM is also poorly performing quite poorly here. So this is something interesting to note, is that this change between point and sequences. So yeah, this was what I just said. Then we can also look the difference between the ratio. So let's measure the difference between time series that have like less than 0.001 time series, anomaly, sorry, and above 0.1, so above 10% of anomaly. So here also there is a big difference in the rank. So you see that, for instance, here, Norma is ranked 2 for a very low ratio. Norma is ranked here. So there is a big difference of performances. I4S also, I4S is like here and then first here. So this difference in the rank is something that is very interesting. So there is like an heterogeneity of results based on the different type of time series. And this is something to take into account in the future. But in general, so these are like 4 examples. So these are like the ECG, MGAB, Yahoo dataset, and Daphne. And these are the performances. So box plots, because there are like multiple time series in these datasets of PR here. And then what we see is that based on the dataset, we observe very different ranking, very different performances. In this MGAB dataset, log and AP are working very, very well. Whereas on the ECGs, Norma is performing very well. And then you see that it's never the same. I mean, it's very hard to find like one very consistent model for multiple different cases, which is very motivating for future work. We will see later, but there is no overall winner. So this is also a conclusion of TSB and also a conclusion of time eval, that when you look at the plot of the different performances based on the anomaly type, it's never the same best approach that is working for every type of anomaly. Okay, so this is about the experimental evaluation, and now I will try to, yes?
So many of these approaches are unsupervised.
Yes.
And isn't it kind of in the theory of an unsupervised method that it cannot work on all anomalies?
Yes, I mean it's not surprising, but it's nice to have this observation and to say clearly, like, look, okay, we have these results and we see this performance. We could have thought that distance, computing DTW distance between subsequences might work for every cases. So now we know that no, it's not working. But of course, when you have like your you're only using general statistics, like either distance or density measure, it's difficult to adapt to every possible cases. So it's not a surprise, but it's what is a surprise is that it's like very heterogeneous. I mean, when you look at, let's go back to the here. When you look at this box plot, then the range is huge. I mean, you move from 0 to 1. So this means that you either fail completely, and by completely, it means that you say that the normal behavior is an anomaly and the anomaly is normal. 2, succeed completely. This is very interesting. So this big range means that there is like there is work to do on maybe proposing more consistent, more stable method for different games. It would be very interesting, for instance, to propose a method that is not good for all, so it's not the best, but actually with a very low Y. So you can say, okay, I will not be the best, but at least I will never be the worst. So this is also like interesting future work on time series. So trying to go into towards this direction. So, okay, so here I showed you results, experimental results. So we used like different evaluation measures, but I didn't define them. So I said OC-ROC, OC-PR, but you know, these things are not all the time easy to understand. And what are the challenges for time series? So evaluation measures, I will try to describe you, give an overview of what we can use for time series. Okay, so here you see again a very nice time series with anomaly score here. So as I said, we have labels and we want to evaluate the performance of this anomaly score on these labels. Okay, so one simple way is to say, okay, let's find a threshold value. This threshold here, when we have a look, then this corresponds to this thing. So here we can divide multiple things. We can say, okay, here are the correctly identified anomalies. So we call that a true positive. Okay, so this is not for time series, this is in general, but this is like the terminology. Then the anomalies that have been not detected are called false positive. Sorry, false negative. False positive are the one when you say that it's abnormal, but it's not. And then true negative here. And with all these values, you can actually build compute values that kind of takes the best of both. So you can compute the precision, which is the ratio of the detected anomalies among all the detection made. The recall, which is the ratio of correctly detected anomalies among all the anomaly. So precision is here, this ratio here, recall is here. False positive rate is also useful. So how many false positive you have on all your normal points. And F-score, which like kind of takes the best of both precision and recall. So there is a beta parameter. Usually we use 1. So F1 score. So we have like precision divided by precision plus recall. Okay, so these are like very well-defined studied measures, not for time series, for classification, clustering, maybe not clustering, anomaly detection, not for time series, but also for time series. So we can use them. But here the problem is, how do we define this threshold? So this threshold is not something easy. If we say, okay, let's cut here, then you have like a very different results. Also, if you say, okay, let's take only very the most abnormal sequence here, you might also like miss important anomalies. So defining this threshold is difficult. So it's might be possible on supervised manner. So if you have like labels and you can actually supervise it and choose the best threshold based on your training data, it could work. But on unsupervised settings, it's very hard to set this threshold. So it's mandatory for use cases. Huh? I don't mean that we should not use threshold. It's mandatory for to detect like precursors of vibrations. At the end, you need to extract them, so you need a threshold. But for the evaluation, we can use actually area under the curve based evaluation measure. So area under the curve is pretty simple. You take one threshold, you compute the true positive rate and the false positive rate. Then you move the threshold down, you compute again the point, you move it down, you compute, and then you do it for a lot of value of threshold, you get a curve, this curve here. So here, this curve is a receiver operative curve. I'm correct? Yes. It's operator, operative. Operator, okay, thank you. So it's a ROC curve, and then we can use the area under this ROC curve, and this area will be like our evaluation measure. So what is nice with this kind of measure is that it kind of average well, it's not really an average, but kind of average the performance for all the possible thresholds. So you don't need to define a threshold here. You can kind of obtain a value of the performance of this score without saying, okay, let's use 3 times the standard deviation. Let's use like this thing. So this is very nice. You can also use something called OCPR. So this is the area under the precision recall curve. But this is the same principle. Okay. So these are like 2 very basic measures. And now let's talk about the issues related to time series. So for points, for tabular data, it's easy. You have like a row, and this row is a normal or abnormal. Okay, and then you can compute precision, recall, and everything. But for time series, here, the expert said the anomaly is here. And then the score saying, okay, and this is this. So is this score perfect? So for some people, this could be actually very nice. I mean, you are a little bit before, but you are still like identifying the anomaly correctly. But here, 80% of the points, so the precision will be 20%, and the recall will be 20%. But is it really the case? I mean, in this case, and now let's imagine the case that, sorry, the expert, the engineer or the doctor said, okay, the anomaly now, it's not here, it's here. And then this change, this slide in time, this alignment of the labels changed significantly the performances. Even though between this and this, there is not a big difference. Here, the anomaly is correctly detected in both cases. So why, in one case, one method should be completely discarded compared to the other? So this is like this alignment problem is very important. And in time series, so this is the case for 2 reasons. First, labeling strategy. The labeling strategy might be different between domains. Doctors might say, okay, I label only the first point as anomaly of arrhythmia, and then the rest is not. Okay, maybe you see here, for example, IOPS, sensor scope, and the Numenta benchmark. On IOPS, the guys that generated the benchmark said, okay, the anomalous points are only the points that go up. On sensor scope, they also included the right border. And on NAB, they included both the left and the right border. So these different labeling strategies are an issue. I mean, how can you evaluate consistently on different data sets? You need something to actually take this into account, because then you also have methods. So point-based approach will most likely give scores like that. So with, okay, I say like this point is abnormal, I give like the point rise very easily and go down very easily. But for subsequences, this point is already contained here. And then it goes down and continue. So the subsequences will give score that looks more like that. But in this case, this is this point that is detected, even though the values are here. So if only this point is labeled, then a subsequent method that will say there is an anomaly here will be wrong, even though it should not be wrong. Okay? So this problem, these labeling strategies, difference of labeling strategy, misalignment between scores, between methods, so LOF methods might usually detect the beginning of the anomaly. NP the same, Norma is more like this white thing because they catch the anomaly since the very first point. So this is a big challenge for time series. So trying to deal with alignment. So there exists different measures that have been proposed. So a first method, so this have been published in 2018, sorry. So this is like a range precision and a range recall that try to catch actually this misalignment and give to the user the possibility to tune it for their specific use cases. So here, the recall is basically the average of the recall for all the detected the anomaly. And then for the anomaly, they define an existence reward and an overlapping reward. Existence reward means, did you detect correctly the anomaly? It means that, is it like at least 1 point that overlap? So yeah, you found it. And then overlapping reward is a way to say, okay, is it important for us to be like very overlap? So is it important to be like that or like that? So this alpha actually can say, okay, no, it's not important to be here. It's important it's not important, sorry, to be like very overlapped. It's just important to find it. Okay. So this is a possibility. And then they created like, they also try to reward based on the position of the detection. Yes, because for anomaly detection, anomaly prediction, eruption detection, it's easier if you detect the eruption before than after. So here, it's better for a method to detect here than here. So you can actually give value with this tunable function to saying, okay, I want to give more reward to the method that actually detects the anomalies before. Okay. So these are like tunable measures. So there are like a lot of parameters. So this can also be a problem. I mean, when you want to evaluate a lot of methods on a big benchmark, you don't want to tune for all the time series or each time series. So this can be a problem. So we also proposed another kind of measure, which is called volume under the surface. So in the VLDB 2022 also. So in this case, the philosophy is a little bit different. So we don't have any parameter. The point is just, okay, we know that some method might detect a little bit earlier, a little bit after, even though they are still detecting the same anomaly. Okay, so one solution is say, okay, let's include a small buffer region before and after the anomaly. So here we have like 0, 1, but sorry, instead of having 0, 1, we'll have 0, and then it rises a little bit, and then so it's kind of limits the fact that you will completely discard one method because it was just a little bit before. Okay, so this buffer region, unfortunately, is a parameter. So this is not nice because we don't want parameter in evaluation measure. So what you can do is actually you can change the value of this parameter as you change the threshold value. And then instead of getting like a curve, you get a surface. So you get a surface for both the threshold and this buffer region. And your accuracy measure will be the volume under the surface. Okay, so this is a way to actually try to say a parameter-free method. So in practice, it is not exactly parameter-free because computing for every possible buffer length is not scalable. So we can reduce saying, okay, we want between this value and this value. But it's a nice way to actually like be more flexible, more tolerant on the different methods. And what is also nice that you can use it for both Oak Rock and Oak PR. What you just need to do is to change the buffer region. Okay, so this was one attempt to propose like a new evaluation measure specific for time series, and this is very interesting. So if you're interested in time series and anomaly detection, I suggest to have a look at this measure, also an estimate method. Yes.
So with this measure, I actually try to use it, and doesn't this punish very accurate algorithms? For example, I had the issue with the forest methods.
Which
do have a very sharp line of anomaly goes up, anomaly goes down.
Yes.
And it doesn't include buffer region, so it gets punished for not including buffer region.
That's right. Yeah, that's actually a good point. Yeah. But which point? I4S, which point you used?
Subsequence.
Subsequence. Well, subsequence, there should be a buffer region at the beginning. Well, it's rare, but the thing is like either method will be here because there are subsequences, either there will be here because there are points, either there will be here for some reason that I don't know, but they could. So the thing is like they are punished, but they are punished the same way as the subsequences that meet this part. They're actually less punished. In a way. Actually, this is what we observed. But for instance, normal will be we say something. This is the score on normal here. So this is the score of I4S actually. So this is I4S subsequence. Here you see it starts here because of course the anomaly starts here. So you have value here, but it stops here. Here there is 1. So it's actually more punished because of this than this. Then I agree with you. This is the problem of this value. You can change this value to actually less punish or be less punish the one that actually have no values here. But what we observe in general is that it's punished everybody the same way. More than it punish more one method that it doesn't force all the methods to have values here. This is what I mean. And what happens usually is that methods are more missing points here, but the fact that we give a little bit of credit here is like reducing the difference. So we did like a lot of consistency measurements. So like trying to change the lag. So we lagged a little bit the score and see the variance of the values. And we saw that for views, there was like very little changes when we do lag. So you lag a little bit the anomaly score from the left and from the right, and the changes are very small compared to other methods. And this is because of this region. So it might punish, but this is actually a nice point. I mean, this is something that we should study. I'm not saying this is perfect. We should continue working towards this direction, but the buffer region is an idea actually to be more flexible. All right. So we are reaching almost the end. So let's try to conclude now and discuss about like open problems. So first, if you are interested in anomaly detection, I suggest you to read this paper. So the first one is a time level paper. So this is like the bench proposing both the benchmark and the experimental evaluation. This is a very nice work. Like a lot of work have been conducted here. So there is also a GitHub. So the code is open, everything is open, so you can actually get access to this. There is also the TSB benchmark. So again, the paper and the GitHub. There is a AMON benchmark here with also some material here with the datasets and some implementation. And also there is a survey. So a survey that lists all existing methods. So this was a little bit earlier of all this work, but these are still interesting. So these 4 papers are, you can actually, if you're interested, go over them and check the code to give you to have your own opinion on what is the best, what is the thing. So these are like nice works, and among them, like 2 are in VLDB. This is TKD, and this one is an HCM survey. So now about open problems. So I said in the introduction that what we define as an anomaly is a rare events. Okay, so it's something like daylight, flooding, snowstorm. So these are like real anomaly. So one question is, what happened? What do we do with this? Okay, so this is clearly an anomaly for us. I mean, for the one that actually for the algorithm that take the time series, but it is not for human. This is Christmas. Okay, so one question is, how can we do context-aware unsupervised anomaly detection? So maybe it will not be unsupervised in this way, but actually, how can we actually get more context, give more context to the methods to kind of avoid detecting it as the most abnormal pattern in the time series? So this is one interesting future work, one interesting lead that you can follow if you want to work on time series. So this is a big problem for many domains. For example, so in the energy production domain, so with power plants, so when I worked there, so you have like the energy, you have like each sensor measurements. So these power plants have to start. So they have to shut it down to make some maintenance and then start it again. So this start is an anomaly. It's like happens like one every year. So it's an anomaly, but no, it's like there is context here. We know that it starts, and even more difficult, there is maintenance operation during the process. So they reduce a little bit the power to do the maintenance, and then they increase. But this is known by the logs, by the expert. And this for the engineer, when I say, okay, this is my method, and they detect these events that are known, this is like a very low value for them. So adding context and removing this kind of anomalies on a smart way could be very interesting and very important. Yes.
So when you say including context, Christmas happens every year, right? So if you can view larger windows, then it's naturally you can see that there are many Christmases.
Right. Yeah.
So like it depends on how big is your context.
For sure, this is also this would be a solution. Yes, to increase the size. Yeah, but still it will still be an anomaly compared to a regular day.
Right,
but it is also by definition. Yeah. Yeah. Yeah, right. If you look at years, this would be the same. But if you want to look at unusual days, like to detect floodings or snowstorms, or to detect like impact.
I cannot predict snowstorms.
Yeah. But you can measure it from the data, trying to extract patterns and trying to extract information. So the point is not to predict it. The point is just to make some correlation to say, okay, there is an impact here.
So if we have huge windows, it's like a solution, but Christmas is not predict.
Yes, right. Yeah, this definitely this is the scale of the window you are looking at make a difference. All right, so this is like one interesting open problem, and then there is like another one. So we were discussing about this. So what about ensembling? Okay, so one very interesting point here is okay, we observe that there is no overall winner for different data sets. So when you look at the overall results, so this is one of the views measure, and the inference time here, so the execution time of the method. Okay, the question is, can we actually build an ensemble method? So trying to fight this fact that there is no overall winner of unsupervised methods, and trying to propose like an ensembling approach that get all try to get the best of both. Okay, the best of all. So this blue thing, green thing, sorry. is like one very simple assembling is like you take the anomaly score of everything and you do an average. Okay, so this is an interesting assembling. It's like slightly better than the rest. Already doing this is improving the result, but the problem is on the execution time. You have to run all the methods to get the score and then compute the average. Okay, another solution that is very yes.
A question to that. Do you or how do you normalize these anomalies before you compute the average? Because they are not all between 0 and 100%, and they typically also, like, if you look at the distributions of the anomaly scores, they are so quite different. Like for example, we said for the isolation power, it goes like up really fast and down, but like for other methods, you have like more continuous curve.
So what is interesting here is that there is nothing. I just do 0, 1 normalization and average point. And
just do a min-max and then
yeah,
you do the average.
yes, it's just simple. Of course, there is smarter way to do it. I'm not saying that this is a solution, but it's just doing this is already like reaching top performances. So there might be like very interesting work. You are working on this actually?
A little bit.
Okay. So this is very interesting. Yeah, there is like a significant margin of improvement. Okay. So second point is, what about automatic model selection? So here, what I plot here in white is an oracle. Oracle is basically, let's say that we have at our disposal a method that always selects the best method for each time series. Okay. This would be the performance. And there is a huge difference. There is a huge difference. So the question is, can we actually train a model to select automatically the method and select only one method such that the execution time is in the same order of magnitude? So instead of running everything, you need only to run one, the one you've chosen, and try to choose it correctly, of course, the most accurately. So this is a very interesting also future work. So I think it was 2 days ago, there was like on the AI and DB session, a talk about compression algorithm. So how to select automatically compression algorithms. So this is actually exactly the same idea here. So one way is to do classification. So you just classify the method and then you try to predict the best method. What they did in compression is very interesting. Actually, they try to do a regression to predict the score of the method and then use this regression like only a max. And this could be also a very interesting solution. So I'm actually looking forward to try to apply this and see how this could perform. So these are like the two open problems. I said I was doing 1.5 hours. I'm exactly 1.5 hours. So these are the references for this paper. And if you have any question, any more question, feel free to ask and I can try to answer. The question. We already covered a lot of questions, so that's no problem. But I have questions. So you are working on ensembling.
So I'm working in change point detection.
You know?
Change point detection.
Ah, okay.
But we know Paparizzos.
Yes.
So this is a colleague of mine.
Okay.
I'm actually doing a PhD like under him, or he influenced me, and we've worked on this XUCR data set from here. We've worked on the competition like that. So that's when we work a little bit in anomaly detection.
Okay, right. Okay. Do you know? Because I will join a group that is developing Rupture for change point detection, like a GitHub package called Rupture.
Yeah, sure. Yeah.
Okay. Well, that's interesting.
From Twan at our package.
Yeah. I'm joining their team in 2 days.
Oh, really?
So no, this is an interesting topic. And you are also working on
I'm working on
multivariate anomaly detection?
Yeah.
And in the Asso-Plattner Institute?
Huh?
In Asso-Plattner Institute?
Yeah.
Okay, so with Throsten? With Throsten?
Yeah, but Throsten is no longer in the Asso-Plattner.
Yeah, right. I know he left, but you are working also with him.
Yeah, kind of. So I'm working with Sebastian, and I'm supposed to greet you. I sent him a screenshot. Hey, look, I know this paper.
Yeah, I mean, a lot of work have been based on Sebastian work. So.
Just to see if we have any question.
So what are you? I'm curious actually. What are you doing on multivariate?
So I guess you could look at the page of that. You said you want to context, and you could add a multivariate, another time series dimension that's
That add context.
with 0, 1, for example. But the issue is that
Continue, I will tell you later.
they're all awful.
Yeah.
And for example, in STEM,
Yes.
in their paper, they state their method doesn't, or any method, doesn't scale above 5 dimensions. And then they said the method to deal with it is choosing the top K dimensions, and then they never state how they do it.
Yeah, right. This is the problem of.
So what I'm trying to do is find kind of univariate algorithms to make their case, because you can obviously just apply to the dimensions and average it or max it. That's kind of my idea. But instead of doing it in a univariate case, I'm doing multivariate. But I'm splitting the large multivariate time series that have like dimensions, splitting into correlated clusters of dimensions,
Right.
and then only running it on the correlated.
Yeah. So I was wondering if you worked with. Okay, maybe I can answer this question and then I go back because I have a lot of questions. Yeah, I can share the slide, of course. Yeah, I can put it. Maybe Themis will put it on his website for sure, but I can also share it. I don't know if there is a way to share it on the EDBT webpage.
I don't know, but because I wanted to, I will take it and will find a way, maybe within the site.
Okay.
Okay.
Okay. Well, I will try to put it on my website and so you can have access to the slides.
I think we already exchanged by mail.
Maybe yes.
About explaining.
Yeah, right. Yeah, I remember.
Very nice. Very interesting and. Do we know? I'm sorry. But maybe. And then apply just what is the right reference. In fact, if it's a new time series that you can match with. Right. You have some kind of reflexive approach to say, okay, I'm trying to reconstruct my anomaly. No, then it's a real anomaly, that has some kind of.
Yeah, I think it's pretty interesting.
Yeah, I was wondering, and other dumb question, but why I didn't ask. If you know afterward, you compute, you have observed that your signal is like this, you have predicted some other signal, then you should take it.